40. Okay.
Yeah, yeah.
Okay. Great. So today what I wanted to talk about is to go through some of the motivations for like what kind of data structure and what kind of cryptographic structure makes sense for the Ethereum state tree. And like talk about some of the thinking that we've done going from hex trees to binary trees to Verkle trees to cryptographic accumulators, other kinds of fancy algebraic constructions, snarks, and basically just explain kind of what are the very specific properties that we're looking for from a state tree and how the different options that we've considered compare with each other, and like basically why the Verkle tree looks like the most attractive out of what we've seen so far, how some of the other options look, and like what kinds of structures might state trees be used for in the future. So start off the current Merkle-Patricia tree. So this is the structure that is used for in the storing the Ethereum state today. So every Ethereum block contains a bunch of roots. One of those roots is a state root, and the state root is the root hash of this tree, and the tree has a hexary structure, right? So every node has 16 children. Every node is the hash of 16 children, actually up to 16 children. So if there, like for example, there's no addresses at all whose hash starts with a 7, then or whose hash starts with a 5, but then there might be 14 children instead of 16. But most nodes that are not right at the end in practice tends to have 16 children. So nodes have 16 children, and then every node is a hash of some child nodes, and then child nodes are hashes of other child nodes, until eventually at the bottom you get to the leaves. So the reason why we have the state tree is so that every block can contain this hash commitment, and from that hash commitment you can then make a branch, and that branch can prove any individual value. So like, for example, here, if you want to prove this value 27 inside of account 175, then you can make a branch that consists of the portion of the tree that goes down from the state root to the 27. And those values can actually be combined together, and the nodes along the way, they can be verified together, and as long as every step is the hash of the values at the level below it, then you can verify just without one branch that 27 actually is the object in this particular position in the state tree. So the long term, I guess medium term at this point, goal that we want to achieve is this idea of stateless clients, right? So we want it to be possible to verify an Ethereum block without having the entire state yourself. So if you don't have the entire state yourself, then if you have a transaction that accesses some state, well, how do you verify it? So this is where we use these proofs, right? So if you have a transaction that touches a few accounts, then in order for stateless clients to verify it, someone has to package a block that comes together or together with the Merkle branches for every single object. So a bunch of accounts, a bunch of storage keys that particular transaction touched. So these stateless blocks, they're going to be much bigger than regular blocks because they have to have these extra proofs attached. But the benefit is that you do not have to have any state, right? So you as a node can just join and you can start verifying a block immediately. You do not need to do any syncing. You would only needs to do syncing if you actually care about like getting historical data or actually having some large piece of the state locally because you just want to like run some script on it or something like that. Right, so just to verify the chain, you would not be required to have state. You would be able to start verifying immediately. You would not even have to verify blocks in order. You could only verify a block if some node raises an alarm about that block. Stateless clients technology is also used in fraud proofs. So a lot of important just use cases and benefits for stateless clients. Another thing, of course, is that if we ever want to zero knowledge proof blocks, then the zero knowledge proof prover is not going to have access to the entire state, or the verifier is not going to have access to the entire state. And so like, you would want the thing that would be proved basically the prover would have to prove over verifying a block the way that a stateless client would regardless, right? So there's a lot of benefits toward moving towards stateless clients, just reducing dependence on disks, making it easier for more people to run nodes, making it more flexible. So validation, instead of being all or nothing, you can verify some blocks and not other blocks. But I've talked about all of this a lot. The important point is that for stateless clients to be possible, the sizes of these proofs, so what we call witness sizes, they have to be reasonably short. So how short? Well, we can look at the properties of branches in Hexa trees as they exist today, right? So if we want to look at the length of a single branch, then the length of a single branch on average is roughly 128 times log n. Now, you might ask, well, why this number? So it's actually 512 times log base 16 of n, because at every level of the tree, every node has 16 children. And so if there's, like, say, n nodes in the tree, then the depth of the tree is going to be log base 16 of n. So say if there's 16 to the power of 5 nodes in the tree, then level 1 will have 16, level 2 will have 16 squared, level 3 will have 16 cubed, level 4 will have 16 to the 4, and then level 5 will have 16 to the 5. And then log base 16 of n just equals log of n divided by 4. And then because every node has 16 children, and a Merkle proof actually has to include all of the children that make up each node along the path, so that you can hash these nodes together and verify that the hash actually matches. And so, like, basically, at each one of these levels, the proof has to contain all children. So all children of this guy, all children of this guy, all children of this guy, and then all children, each child is 32 bytes, 32 multiplied by 16, 512. But then because log 16 of n is log of n divided by 4, so we divide by 4, go back to 128 times log of n. So for example, if the state tree has a size of 2 to the 30, so about 1 billion, then the length of a branch is going to be about like 3.8 kilobytes. The cost of generating a branch is going to be basically log of n over 4 database reads. So the data for our branch is already in the database, and so you just have to read it a bunch of times. If you want to do many branches, then the formula becomes roughly basically this multiplied by k, except instead of log of n, it becomes log of n over k. Basically, you get to save a little bit, because if you make lots of branches, then they start sharing hashes at the top, and so you get a little bit of savings, right? And then the cost of editing one branch, right? So this is if there is one block, and then that one block actually changes a branch in the state, then how much work does a node have to do? And in this case, you have to basically redo a bunch of hashes. So like you say, if this 27 becomes a 28, then you have to rehash this node, you rehash this node, you rehash this node, you rehash this node. And each of those hashes is 512 bytes. And then also on top of this, you have to do log n over 4 database writes. So that's where we are right now. The main problem is that branches are too large, right? So for example, if we look at a block that has 15 million gas, then 15 million gas divided by 21,000, which is the cost of a basic transaction, that gets us to about 715 transactions in a block, I think. 715 transactions, and then each transaction has a to and a from. So we're talking about 1,400 addresses. 1,400 addresses multiplied by this gets us like around like something like 6 megabytes. And then that doesn't even, and that's not even the worst case, right? That's and then go down a bit because of this log n over k thing, but still like around 4 megabytes. It turns out that that's already a little bit too big. And that case is not even the worst case, right? Like there's much worse cases where you have certain types of transactions that are much heavier on state reads and state writes. And so the witness sizes get even bigger. So the challenge is, can we make these branch sizes smaller? So one very simple thing we can do is we can go from hexary to binary. So the reason why going from hexary to binary is better, right, is if we zoom in on just a particular set of 16, like in this case, it's just a set of 8, right? Well, like, let's look at it. if, let's say, this was a node where you just had 8 nodes in parallel, then if you want to prove that this hash is the hash of a node that contains this value, you'd have to provide 1, 2, 3, 4, 5, 6, 7, right? You'd have to provide all the sister nodes so that all the data can get hashed together and generate a hash. But if the tree is binary, then you have to provide fewer hashes, right? You just provide this value, and then this value, and then this value, and then this value, right? So instead of providing these 7 sisters, you only have to provide 1, 2, 3. And then if we go up from 8 to 16, then instead of providing 15 sisters, you'd have to provide 1, 2, 3, 4, right? So with binary trees, basically the number of layers goes up by a factor of 4, but the number of sisters goes down by a factor of 16. And so on net, it's going to be 4 times, the proofs are going to be 4 times smaller. The hashing is going to be a bit less. So binary is already a significant improvement over hexarray, right? So the branch length goes down from 128 log n to 32 log n. So once again, right, the depth goes up by a factor of 4, but the number of sisters at each level goes down from 16 to 1, or from 15 to 1, I guess technically. So it's altogether a factor of 4 efficiency. The cost of generating a branch. Now, you can actually get a little bit clever here. So the way that Ethereum, like the kind of most existing, somewhat fairly naively designed Ethereum clients work is they just store the data, like they make each node in the database corresponds to one node in the hash structure, right? So like because you have a single 512 byte node that gets hashed together, you store that as one unit. But you don't actually have to do that, right? On disks, you have a page size of 4 kilobytes, and so it's basically about as expensive to fetch 4 kilobytes from a database as it is to fetch a much smaller amount of data. And even going up to fetching 8 kilobytes, it's only a little bit more expensive than fetching 4 kilobytes, right? So hard drives are really actually optimized for making big reads. And so when you store on disk, you can, even if the tree is binary from the point of view of hashing, on disk, you can make it a base 256 tree, for example, right? Like you can just store lumps of 256 nodes all in one single node, and then you just pretend it's a tree of width 256, except instead of hashing a node just directly, you hash it by making a mini Merkle tree, and instead of and then like when you make branches, you get to optimize some more, right? So with binary trees, like you get somewhat more flexibility. With hexarray trees, you sort of can, except with with hexarray trees, you have somewhat less freedom because like you still have to grab pieces of information that like the database nodes have to contain like individual nodes that are being hashed, but with binary trees, the nodes that are being hashed are smaller, and so you just have much more freedom in terms of like what the size of your database chunking is. So you get some benefits here. K branch length. So once going up from a single branch to K length, once again going down from 128 to 32, factor of 4 difference. And then editing, instead of these big size 512 hashes, you're hashing 4 times more nodes, but the hashes become 8 times smaller, right? So binary trees are an improvement, but the problem is that binary trees are not enough of an improvement, right? Like these numbers are already much better, but the numbers are still not good enough, right? Like we're still talking about these multi-megabyte witnesses in the worst case, and we really, really want witnesses to be significantly smaller than that. So what can we do, right? So we could use polynomial commitments, right? So polynomial commitments are an algebraic alternative to hash-based structures for committing to large amounts of data, right? So, and I'm sure people in Ziki study clubs have seen the equation for a Kate commitment witness before, right? The Qi equals P of x minus the y coordinate divided by x minus x minus the x coordinate, and stick that into the an elliptic curve point. And this just is this one single witness that you can use to prove that P of xi actually does equal to some particular value, right? So polynomial commitments, they're algebraic, they're nice. They have this really nice property that it seems like no matter how big the polynomial you're committing to, witnesses have a fixed size. You just a witness is just a single QI. It's just a single point. So can we use witness polynomial commitments, and specifically Kate commitments, to do better than binary trees? So let's go through the properties, right? So the length of a proof, it's not a tree anymore. It's just a polynomial commitment. The length of a single branch goes down to just 48 bytes, right? If they're BLS 12 through 81 points, they're 48 bytes long. And so a proof is just going to be 48. It turns out that if you're going to prove for k items, then your proof size actually is also just 48. Well, it's 48 plus the data that you're proving, right? So the data you're proving, so I probably should just say plus 32 times n here, but then add, but you only need this one extra witness, right? You basically get, like, instead of dividing by x minus xi, you divide by the product of x minus x1, x minus x2, x minus x3, and instead of just a p of x1 here, you provide like the interpolant of a bunch of values, right? So like, I'm sure the math wizards have seen this before, right? But the point is that you can make a witness for as many values as you want for just the data itself plus 48 bytes. The cost of editing one branch of the proofs, right? Well, you just update the data. So far so good, but there's this one problem, right? Which is the cost of generating a proof. In order to actually compute one of these quotients, you have to actually do polynomial division. This is a degree n polynomial divided by degree 1 polynomial. And this is an O of n operation, right? And here we're talking about n being a billion. So this is just completely ridiculous and impractical. So so it seems like we have a problem, right? But the math wizards among you may have also remembered that there exists this magic algorithm where you can pre-compute all the quotients in n log n time, right? I think it was like the paper is like FC20 or something. There's some acronym for it, but Dmitry Kravadovich did some work on it. Dankrad did an implementation. It's a really amazing and lovely piece of math, right? So you might wonder, well, look, yeah, you can pre-compute all the witnesses and then in O of n log n time. And if you generate all the witnesses in n log n time, then you don't actually have to generate the witnesses anymore because the witnesses are already there. Problem is that this does not work. Now, you might ask, well, why does this not work, right? The reason why it does not work is because when you edit the data, right, you basically have to do the pre-computation all over again. And the thing with state trees is that state trees get read very frequently, and they also get written to very frequently, right? Every block reads thousands of values from the state tree, and every block makes thousands of writes to a state tree. So it's definitely the like sort of a case where you don't want reads to be super expensive and you also don't want writes to require recomputing the entire data. So unfortunately, this is also prohibitive, right? So you can do it without pre-computing witnesses. In that case, computing witnesses is prohibitive, or you can pre-compute the witnesses. In that case, editing the data is prohibitive because you have to recompute all the witnesses every block. So polynomial commitment schemes are just not designed to deal with large polynomials that are constantly changing, right? Now, it turns out that there is one last trick up our sleeves. We can try to do some even more clever math to try to rescue polynomial commitments. So this is this ETH research post that I made, I think, I guess about a year and a bit ago. Basically, we can actually do a square root of n compromise between the two. So we can split up the state polynomial, and you don't have to do this in consensus. Clients can actually do it locally. Clients locally store the old state polynomial. So this is a polynomial that gets reconstructed and witnesses get reconstructed. And this is done every square root of n steps. And then you have a recent deltas polynomial. And the recent deltas polynomial just contains changes to the state that were made very recently, like within the last square root of n steps. And witnesses from the recent deltas polynomial get generated in real time. There's this really nice algebraic property of Kt witnesses that a witness, if you generate a witness against A and you generate a witness against B, and you just add the witnesses together, you get a valid witness against A plus B, right? So we're going to use this property, right? Basically, the clients are going to store this old state, and they're going to regenerate it, and they're going to run this process in the background, so it's amortized, and they're going to regenerate the full state and all the witnesses every square root of n steps. And then if whenever they need to generate a proof, they're going to use one of the pre-generated proofs against the old state, and then they're also going to use just generate a proof against the recent deltas, which is this much smaller polynomial. Well, smaller in the sense that the non-zero evaluations are sparse, right? And that's a kind of smallness that's actually good enough for us. And then you generate these two witnesses separately and then add them together. So what are the properties here, right? The cost of generating a branch. So generating the old state branch is trivial, but then generating the new state branch requires size square root of n arithmetic and elliptic curve work, basically because from the recent deltas it's polynomial, you have to just regenerate the witnesses every time. And then the cost of editing one branch amortized is going to be square root of n log n, because you have to keep running this background process that regenerates the entire O of n witness set every square root of n steps, right? So we have square root of n over here, square root of n over here. But so this is better, but unfortunately, it's not quite good enough, right? It's like maybe like 2 orders of magnitude away from being a super awesome and amazing solution that we can live with, but unfortunately, it's not quite there. Now, of course, like maybe this is the time when like someone like Starkware or some ASIC manufacturer is going to come in and say like, hey, wait, we're going to come in here guns blazing with our super awesome hardware. We're gonna make the square root stuff work. And maybe they will come in and do that, or someone will come in and do that. But like without some kind of breakthrough that just makes all of this like an easier by big constant factor, it's still not good enough. So this is where we come to Verkle trees, right? So a Verkle tree is not a single polynomial commitment. It's a tree of polynomial commitments, where every polynomial commitment has a large size, right? So for example, every polynomial commitment would have a size of, in our design, 256 elements. And then proofs within each commitment are O of one size, right? So each commitment works the same way polynomial commitments normally do, except instead of the data being in a single commitment, the data is in a tree of commitments, right? So like you have a root, and then that root is the root of 256 different values, and these values are all themselves roots, and this is a root of this set of values, and this is a root of this set of values. So instead of one commitment, you have a tree of commitments. And you might ask, well, what's the benefit, right? Well, the benefit basically is that if you want to prove a single value, then you would have to make a proof over here, then a proof over here, then a proof over here. But the nice thing about commitments, right, is that proofs are all of one size. So because each commitment has size width 256, so instead of needing, like, say, depth 32 for a billion item tree, you would only need depth 4 for a billion item tree, and then the proofs are constant size, and so you would just need to have 4 proofs, and the proofs are nice and small, and so altogether the proof size is smaller, but the process of and then to do updates, it's fairly simple. You would just update the data. To generate proofs, you do have to do computation over the sister nodes, but the computation is like relatively simple and fast, just kind of like arithmetic and a few elliptic curve operations. So here's the chart with the properties, right? So the length of a single branch is going to be 12 times log n bytes, right? So instead of 32 log n goes down to 12 log n, basically because because these nodes each have a width 256, and so instead of log n, we go down to log n over 8. And then at each level, you have to provide the intermediate polynomial commitment, which is 48 bytes. And then at each level, you have to provide the proof, which is 48 bytes, right? So at each level, you provide 96 bytes, and there is 8 times fewer levels. And so 96 divided by 8 gets you to 12. So 12 log n is better than 32 log n. The cost of generating a branch is going to require, so log n over 8 steps, right? So because every one of these levels has size 256, so instead of needing 8 steps to go up by a factor of 256, you only need 1 step to go up by a factor of 256. And so same database reads as before, and you also need to do size 256 linear combinations, right? So you have to do a size 256 linear combination, just to sum up a bunch of like elliptic curve points multiplied by the values over here to generate the proof. Do the same over here, generate a proof. Do the same over here, generate a proof. To edit one branch, basically, oh, I think this is actually a mistake again. You don't actually need linear combinations. Like you basically just, to edit these values, you like edit one value in place, and then you can recompute the commitment, and then you edit this value in place, and you recompute the commitment, edit this value in place, and recompute the commitment. So you only actually need log n over 8, just single elliptic curve multiplications to edit. You don't even need the linear combinations. So this is already better, right? And then for k branches, it's basically the same kind of like k times log n over k formula. So fairly similar to binary trees, except we replace the 32 with a 12. And also, the cost of generating a branch does go up a bit because we have to do some extra elliptic curve work. The cost of editing values goes up a bit because we have to do a bit of elliptic curve work. This is all instead of doing hashing. Elliptic curve work tends to be more computationally complex than hashing. But it's not that bad, and we have managed to decrease proof sizes. But we can go further, right? It turns out that there is a very clever, fancy protocol where instead of needing to explicitly provide one proof at each one of these levels, we can provide one proof that simultaneously proves an arbitrary number of parent-child relationships, right? So the Verkle proof now only has to provide the inner nodes. And then there is a single proof that simultaneously proves this parent-child relationship between root and the inner node prefix b, this parent-child relationship between inner node prefix b and the sheep node, this parent-child relationship from root to prefix 4, this parent-child relationship going from prefix 4 to prefix 4c, and then this from parent-child relationship from prefix 4c to the horse node, right? So one single proof proves all the parent-child relationships, and so you can. This gets a lot of benefits, right? First of all, you can get rid of instead of 96, this goes down to 48. Second, because you only need one proof, we can actually switch from using Cat commitments and BLS to using bulletproof commitments and just using some regular 32-byte curve. So that makes the math a lot simpler. It makes the proof size 1.5 times smaller again, right? So we made the proof size 2 times smaller because we got rid of the proofs and replaced them with 1. We made it 1.5 times smaller again because we go down from 48 to 32 bytes. And so we've gone down to basically 3 times smaller proofs. And so altogether, right, going from Hexa to Verkle, here we go down from 128 to basically 128 log n to 4 log n. There is a constant factor of about 200. Cost of generating a branch. It turns out that to generate a branch, you actually don't need, you only need a fixed number of elliptic curve operations. You only need one single size 256 linear combination, and you need 128 times log n arithmetic operations. Log n over 8 database reads, then for k branches, the proof, it's very simple. The size of a bulletproof commitment is a little bit bigger, but it's still logarithmic size, so this is pretty negligible. And then the cost of editing one branch is basically the same. It's just like a few elliptic curve multiplications and a few database writes, right? So basically, all the costs just go down a huge amount. The most important thing of branches go down by a factor of 32 compared to the status quo, which is hexagonal trees, right? So this is just really and incredibly amazing. And Verkle trees are already this very nice and powerful compromise, right? Now, there is another credible alternative to Verkle trees, which is snarked Merkle proofs, right? Basically, with snarked Merkle proofs, the idea is that the proof length is just going to be the data plus one single snark. You just snark whatever the Merkle proof is. And snark is going to be about 500 bytes if you use Plonk. The cost of editing is just going to be hashing. And then the cost of generating a proof is going to be the database writes plus about 400 times log n prover constraints if we assume that we're using some of these really fancy arithmetic-friendly hashes. The problem is to actually do this, we need to properly verify de-risk and do all of the all of our homework on the arithmetically optimized hashes. So long-term, this is a totally viable approach. Once quantum computers come and break everything, then you can do snarked Merkle proofs, which are only a little bit worse than snarked Merkle proofs. So this is another nice option. But Verkle trees are the current kind of assumed path forward. But I guess the point of all this, right, is that coming up with an algebraic structure that does everything that we want is kind of hard, right? Verkle proofs in Verkle trees, they're nice. They're not perfectly algebraic in the sense that, ultimately they are a hash of a commitment of a hashes of a commitment of a commitment, and so there isn't a clear algebraic relationship between some node multiple levels down in the root, and so that does mean that, for example, if you want to make zero knowledge proofs over it, then you are just going to have to make zero knowledge proofs over elliptic curve commitments and over elliptic curve multiplications, which is not the worst thing, but it's also not the best thing. But at the same time, it is something really powerful. It is something that has a lot of these very nice properties. There are also there have been a couple of designs that have attempted to provide for the this data structure that we're looking for more explicitly in a much more algebraic way. There was a design based on n-dimensional polynomials that was done recently, but one of the problems with that design is that the proof ends up having to contain some GT elements, and then the constant factor overhead ends up being pretty high. So it does end up having some issues, and it ends up so far out of everything we've seen, Verkle trees still are the least bad of what we know, despite still having this a little bit of proof overhead that we would rather see disappear. But this is still an ongoing problem. There's still an opportunity to do more work and come up with better designs here. So, but that's that's where we are. That's basically where we are now with Verkle trees. That's kind of the reasoning behind them. Some of the other approaches that we tried and ended up rejecting in order to get to them, and some ideas for where we might go in the future.
Yeah. Thanks very much for sharing.
Let's see. Are there comments or questions?
Comments or questions? From CC, go ahead.
Why there are k-branch length in the snark proof, the snark Merkle tree?
Yes. When there are k-branch lengths in a snark Merkle tree. Well, what's the question?
Sorry. Wait. No, sorry. Yeah, sorry, I got an audio problem. Can you say that again? Sorry.
Yeah. Good.
Yeah, the question is like why there are like k-branch codes in the snark Verkle proof?
Like, what do you mean by when? Like, if a Stark Verkle proof gets used for the Ethereum state tree, and then there's like a block that makes 1,000 accesses, then you're going to have to make a snark of 1,000 Verkle branches, right? Which is still a single snark.
Yeah. Right, but they are like witnessed option, right?
Right. Well, basically, well, you don't have to provide the witness. Like the snark itself is just a proof that the witness exists. Like you provide the snark instead of the Merkle branches.
Yeah. Okay. I see.
Yeah. Yeah.
Yeah.
Now, I mean, I think technically, there might be a ration. Like you might want to still provide the Merkle branches for the data that was updated. If you want to like help nodes get an updated tree, but like I think like theoretically you don't have to.
Okay, that makes sense. Thanks. Any other questions?
Is it possible to create sparse Verkle trees with proof compression, as you can with Merkle trees?
By proof compression, you mean snarking or something else?
If I recall correctly, there was a post on proof compression on the ETH research blog, I think by you actually.
Oh, do you mean do you mean this is like the stuff to do with these efficient proofs, for like efficient multi-proofs?
Yes, it was on the ESMT's post.
Right.
It's where you pre-compute hashes so that you can efficiently do proof of exclusion or range proofs, or various proofs can be compressed that way. Can you do the same thing for Verkle trees?
Oh, I see. Range proofs for Verkle trees. Interesting. Well, no. Well, proofs of exclusion you can definitely do, right? Because like you would just like kind of walk down the tree, and then at some point you would walk down to a node, and you would see that one of the nodes has an empty child, and so a range proof, like you would just like. I think if you just provide the proofs to two adjacent nodes, then that already also satisfies as a range proof or as an empty proof for every key that's in between those two. Just because like at every like whatever the first node is where the two keys diverge, like you're going to have the two children, and the two children are going to have different you're going to basically end up also proving. Oh, no, right. You have to like actually make a little bit of an extra proof to actually prove that the children are in between are zeros. You do have to add a little bit of extra on top. So you don't get it automatically, but it's not hard to do, right? And then the key is obviously they just get proven because once you get down to a single key value node, that by itself just proves that there's nothing else there. So answer is yes, with the one caveat that you do lose the property that a proof of two adjacent nodes is simultaneously an emptiness proof of everything in between them. But I think in practice in the Ethereum context, that's never been a big deal, basically because things get hashed before they get put in, or keys get hashed anyway, and no one really cares about like what the order is of hashes of addresses. But yeah, it's very easy to make a proof of exclusion for a value.
Thanks.
Vitalik, I'm going to have to take quite a few notes on some of these things to understand a bit more. But you had mentioned about quantum technology breaking everything. Would you mind elaborating a little bit more on how to possibly prevent that, or your thoughts?
Sure. So quantum computers break a lot of cryptography, but not all cryptography, right? So quantum computers break anything that depends on factoring or discrete log. So they break anything RSA-based, they break anything class group-based, and they break anything elliptic curve-based, including pairings and including simple elliptic curves. The quantum computers do not break lattices, and they do not break hashes. So quantum computers will break Verkle trees, but they will not break snark Merkle trees. I mean, potentially someone might be really clever and come up with some kind of Frye-based Verkle tree that doesn't, or Frye-based Verkle tree that doesn't break. But like, I think the most realistic post-quantum path is to just make a Merkle tree using an arithmetically friendly hash function, and to just do a Stark on top of that.
Thank you.
If anyone, by the way, wants like materials to read up more on these things, I mean, on my blog, I have articles on Verkle trees and ZK snarks. Dankrad on his blog has a lovely piece on cat-day commitments. There was that ETH research post that I linked. Let's see if I can find the number on the fancy scheme that doesn't quite work. 7520. Those are probably, and then, well, Dankrad's piece on cat-day commitments is, yeah, but CC already linked it. That's the one that covers a lot of the math. And then the other one that I was going to mention is that one is the one that talks about snarks, and it also talks about polynomial commitments. Oh, amazing! Someone has one in traditional Chinese. Oh, and of course, another somewhat fun thing is hold on, bulletproof. I made this kind of picture explainer for how for how bulletproof commitments work. I'm just trying to find it. Oh, there it is. No, bulletproof commitments are what we actually use in the Verkle. They're worth understanding as well.